1981 and stayed on at Scripps Institution of Oceanography for his PhD, working with Russ Davis, finishing his PhD in 1987. From there, he went to the Woods Hole Oceanographic Institution, did a postdoc with Bob Weller, then went on to the University of Washington and has been at Scripps since 1993. He's an observational oceanographer with a focus on upper ocean processes, with particular interests in including eddies, air-sea interaction, stirring and mixing of physical tracers, the effect of oceanic structure on acoustic propagation, boundary currents, and coastal circulation. He's really been a pioneer in observational instrumentation, developing and operating numerous high caliber moorings, towed and underway profilers, autonomous underwater gliders, and profiling floats. That's what he's going to talk to you about today. He sailed on numerous oceanographic cruises, many as chief scientist, and as a prolific writer with something like 96 peer-reviewed publications at last count. He was a member of the Ocean Studies Board of the National Academy and is currently participating on a National Academy study group of the loop current in the Gulf of Mexico. Presently, he chairs the Executive Steering Committee of the Southern California Ocean Observing System, or SCOOS, which is one of the regional associations of the U.S. Integrated Ocean Observing System. And he's on the International Steering Team for gliders for the U.S. Interagency Ocean Committee Glider Task Team. Today he's going to talk to you about observing the regional effects of climate variability with the California Underwater Glider Network. I'll turn it over to Dan.
Thank you. Thank you very much. Well, thank you, Mark. Thank you, Kendra. It's a real honor to be invited to this lecture series. It's great to be here. This is actually the first time I've been to USF, so it has been great seeing the home institution of people I've known for a very long time. And hopefully I'll entertain you just a little bit with what I have to say about climate variability off California, off the other coast. So actually I want to start off with a dedication. I don't know if you all know, but this is Steve Pietrowicz. He died tragically over the weekend, and he was a very important person in ocean observing in the world. He was the Argo program manager, and Argo, to my thinking, is the most important thing that's happened in observing physical oceanography in my career. I'm getting a little choked up, I'm sorry. Steve he was an amazing guy, and I just want to dedicate this talk to Steve. All right, back to an outline. So I'll start with a discussion of climate variability on the U.S. West Coast to give you some bearings about what we care about over on that coast. Use that to motivate why we have started a glider network with the Spray Underwater Glider. Talk to you a little bit about what gliders do. They're a newer technology, and the way they sample is different from the technologies we're more used to. And then I'll use that to use the data to make a product that was just created last year that gives us the mean, the annual cycle, and then the anomalies, climate anomalies, which are really our goal. And then finally, I'll touch on the use of these data in models and perhaps a more national network. So let's start the story with something really important in California. And that is the sardine fishery. And this is a plot of sardine catch going back to the 20s. And you can see in the 20s and 30s and into the 40s, the sardine fishery was extremely important in California. It was a big industry for its time, and it collapsed in the 40s and into the 50s. And the reason I'm starting with this is because this was an economic problem. It was a serious... There we go. Let's take care of that. It's kind of in the way, too. It was a serious economic problem. It was a problem that society cared about. And California did an amazing thing in the 50s, what they decided to do was to address this economic problem that they would invest in science. And it's something I hope will continue to happen, but it was amazing that the state did that at that time. And what they invested in was the science behind the sardine fishery, and that was the beginning of Cal Coffee. Cal Coffee is a program started in the 50s with the express goal of understanding the collapse in the sardine fishery. And it's continued to this day with a series of stations shown here. This array is done once per year, and then quarterly about half of this array is done. And I think it's fair to say it's the longest running continuous time series with an array of biological, chemical, and physical variables. It's an extremely important time series, and it was started to solve a societal problem. And what I'm doing now, I hope, will continue this legacy of Cal Coffee. So one of the lessons of Cal Coffee was not only the pressures that people put on fisheries, but there are natural sources of variability as well. This plot here shows an index of El Niño, an ENSO index in the upper panel, and then a measure of Euphausia pacifica, krill off California. And the correlation isn't great, but there is some correspondence between these two indices, one a physical index and the other a measure of the biomass of krill. And one of the very fundamental lessons then of Cal Coffee was that natural variability matters as well. Another very long time series is the Scripps Pier temperature, which goes back roughly 100 years. Here I have it since 1920. And you can see some of these peaks in temperature. And I put red arrows to kind of point out some of them. And the most recent one was basically from 2014 through 2016, which included an El Niño. You can see the highest temperatures of the record are during El Niños. And it's fair to say that the major source of climate variability on the U.S. West Coast, especially off California, is due to El Niño, and it started at the equator. So people in California, actually my neighbors, care about El Niño. And the reason why is because when there's an El Niño, not only does it get warmer, which people certainly notice if they go in the water, but we get storms, we get rain, and this is an example off of Monterey Bay. And as you might imagine, the folks who live in those houses would care about El Niño. And so when I walk down the street in my neighborhood, and most of the folks know where I work, this is the question they'll ask me. They'll ask me, is it an El Niño this year? And what is it going to bring? So El Niño in our part of the world is widely known. Society cares about it. They want to know what's going to happen. All right, so what is El Niño? I'm not going to do a whole El Niño talk here. I'm sure you've seen one before. But let's just say a few things. It is warm water at the equator that's started by air-sea interaction there. But what we're talking about here is how it affects the U.S. coast. And what you can see in these two pictures of SST in '97 and again in 2015 is that the warm water that's really warm at the equator also extends up the coast of the U.S. Now the question, the scientific question, is how does that happen? How do we get a connection from so far away that changes water off the coast of California? Well, there's really a kind of three possibilities for how that warmth can arrive in our waters. So number one is what's called an atmospheric teleconnection. Kind of a fancy word, but what that means is that the atmosphere changes. There's changes in the atmosphere that cause changes in wind off the U.S. West Coast that may change how upwelling happens. The upwelling winds may weaken. Surely the atmosphere changes because we often get more rain, and you saw the storms that happened off Monterey during at least that one El Niño. So that's one of the effects, is an atmospheric connection between the equator and California. A second connection is called the oceanic teleconnection. That's a connection through coastally trapped waves, waves that travel along the coast northward from the equator to California. They're in the forms of Kelvin waves, if you want to get technical, but in the end, it's a connection by waves traveling up the coast towards the pole. A third way that there's a connection between the equator and California is actually through oceanic advection. Now that's different from a wave because this means that the water actually moves, that there's water, that the flow gets stronger and the warm water and salty water from the south arrive. Now, which of these three processes occur is really important to predictability, and it's important to things like the biology, because if there's a strong oceanic advection, that would bring southern species up off of California, which surely does happen. So these three processes are the kinds of things we want to pull apart when we're observing off the California coast. So how do we observe the global ocean? Well, the way we do it now is globally is with Argo. And Argo has changed the world in my view. It's absolutely the most important development in observational oceanography in my career. And the fundamental change was before Argo, the only way we could get measurements out in the middle of the ocean like this was on ships. And you simply couldn't get this kind of coverage. As you can see, I could pull this down the other day. This is from the 4th of April, and this is the coverage of Argo right now. Nearly 3,900 floats, all of which have measured at least within the last 10 days. You make these dots big enough and it looks like you can walk across the ocean stepping on Argo floats. Now, Argo is great. It has solved a large part of the problem, not all of it, but a large part in the global ocean in the upper 2,000 meters. But now let's see what we have to do to observe regional effects, is we've got to solve the same problem off the coast of California. And as I zoom in, I hope you see there are not quite as many dots right near the coast, and that's because Argo floats are designed to do the global problem. And so the question remains, here's the gap. How can we get the same density of profiles that we need to measure things like heat content and salt content and currents? How can we get that same density in a place that we care about regionally? That's the observational problem we face. And here's a solution. So the solution is an underwater glider. This is the one developed at Scripps. It's called Spray. But it's a member of a class of gliders that are in use all over the world now, including here at USF. The idea is really quite the same as a float in many ways, and different in only a little bit. So the way a Spray underwater glider works is it profiles by changing buoyancy, just as the Argo floats profile. It has a bladder in it, and the bladder can expand with oil, and then the glider displaces more volume and it goes up, or the bladder can compress, the glider displaces less volume and it goes down. And that's exactly what an Argo float does. The difference is that the glider has wings, and so while it's going up and down, it flies on wings. From the lift on wings, it moves horizontally, and we can control its horizontal position as well as its vertical position. So that's the added benefit. It's really a successor technology to floats. We can control where it goes. So that's what we got. They weigh about 50 kilograms, so two people can pick one up relatively easily. It's about 2 meters in length. It's got a wingspan of about 1 meter. It gets to the surface, and it actually has antennas in the wings. And so in the wings, it has an antenna, it has an iridium modem. I have lots of iridium modems in my lab, and then it communicates. It has GPS, and so at that point, it's essentially a really souped-up smartphone. It can send data back and forth. We can tell it what to do, and it goes up and down. As far as what it can measure, it's really anything that's small enough to fit and doesn't take too much of our power. So the kinds of things we use are CTD, that's for conductivity, temperature, and depth. That gives us salinity and density. And ADCP, that measures profiles of velocity. We've got a chlorophyll fluorometer on there, and we're starting to use dissolved oxygen sensors as well. As used off California, we typically profile over the upper 500 meters. We can complete a profile in 3 hours, and during that time, we move 3 kilometers in the horizontal. So what that means is that we move at about 1 kilometer per hour, which is slow. So that has an effect on the kinds of things we can do, because you can walk at 1 kilometer per hour pretty easy, I'll bet. But we are able to do the kind of missions I'll show you in a bit. What that means in the end is we got a horizontal velocity of about 1/4 meter per second, or 1 kilometer per hour is an easy way to remember it. And we go out for typical mission durations of 100 days. So about 3 to 4 months. 5 months is quite normal for us as well. So here's a little video of us putting a glider in the water. This is actually off the coast of Palau, and you can get an idea of how big it is. It's pretty easy for people to handle. We're putting it off the side of a little tiny aluminum cat that has an A-frame, and so we're lowering it down into the water. And things will speed up a little bit here. GoPros are great. Anyway, here's the glider going into the water, doing its first dive. And then it'll come back up. As it gets to the surface, you're going to watch it slowly do a rotation by 90 degrees, and it's going to put its wing up. In just a bit, we'll pan up here and see the wing pointing up, and so now it's doing communicating, getting a GPS fix, and waiting for commands, and here it's going off, and this is the beginning of a 4-month deployment. And if you've got another minute and a half on your hands, you can look this up on YouTube. So that's a little video of a glider being deployed. So relatively easy to deploy. The advantage of this ease of deployment is we can do this anywhere in the world. And so that's what we have done. And so here's kind of a summary of our operations using spray all around the world. We've done operations, a lot of operations in the Western Pacific. 1/3 of our work has been off of California. We've done work in the Gulf of Mexico. There's an active program in collaboration with WHOI with gliders in the Gulf Stream right now. We've done some work off the Galapagos to look at the equatorial current system. And then if you add all that stuff up, we've had gliders out in the water now for over 100 years. In recent years, we average about 10 to 12 gliders in the water at all times. We got 780,000 kilometers of track length and 250,000 dives. So that's what we've been up to. And I'm just going to tell you about some of that stuff. One thing I want to point out before I move on is I did show you a picture of Argo before, right? And Argo had dots everywhere. And you can see with the glider, there's the blue smudges on that plot, or tracks, and they're in very tight regions. So we've actually succeeded in having this number of profiles all in regions we care about. And that's the difference with gliders, where Argo is the solution to the global problem. Gliders offer a solution to the regional problem. So now let's move on to the California Underwater Glider Network. This is a network that was really designed for the basic one-sentence purpose of looking at the climate effects on our region off California. Our goal was really to look at the building blocks of the ecosystem. So we measure the physical properties, temperature, salinity, velocity. And we have some of the building blocks of the ecosystem. We have the chlorophyll fluorometer to get us a bulk measure that's relevant to phytoplankton. And we actually have acoustic backscatter from the ADCP that gives us a bulk measure of zooplankton. Now, those lines are on the traditional Cal coffee lines, and that's both for a couple reasons. Number one is if I didn't do it on Cal coffee lines, I wouldn't survive a walk through Scripps. Number two, there's a great deal of history, and I'm just being flippant, but there's a great deal of history. I've got several decades of data on those lines as well that I can refer to. So there's a great reason to stay on those Cal-Coffee lines. It gives me a geometry that's convenient. The data is all made available in real time because it's sent back by satellite. It all goes out within hours of collection. Its first stop on the way out of our lab is Southwest Fisheries. We have a really great relationship with Southwest Fisheries. They take our data, they put it on their ERDAP system, which is now taking over the world. ERDAP has been very successful for them. Goes from ERDAP then out to a national glider assembly center and then out onto GTS where the world operational centers are able to access the data. We also have our own server, spraydata.ucsd.edu, where we serve delayed mode quality controlled data where any of you can go down there and pick up the data. For example, you can get a full decade of data on one of these lines with one click. So if you really want to have 100,000 profiles on your desktop, you may have it today. And the data, of course, is used in several assimilating models. That's probably the most active use of the real-time data. So these data are out there. It's fully operational. Just to give you an idea of what one mission looks like, here's a glider that's deployed off the coast, right off of my coast, and it's going out on this line. As you can see, it's always adjusting its heading. It's not doing that automatically. That's not any of us doing any control. It's doing those adjustments in relation to the currents it's measuring in order to stay on the line, and it does those constantly. Sometimes there's a little eddy it has to get around, but it does that fine too, and it comes back in, does that line in this case 4 times, back in, there's your 100 days. So it takes about 20 some odd days to do the line. About 3 weeks is a good number to remember. And so we get a section every 3 weeks on each one of these lines, measuring everything I can measure. So what are the things I can measure? Things I can measure. Let's see, is this a pointer? All right, there we go. So the kinds of things I can measure. Now I'm going to get into full physical oceanography mode and look at sections. So, you know, I have weaknesses. We all do. So these are sections of salinity. The horizontal axis is distance from onshore to offshore. The vertical axis is depth from the surface down to 500 meters. And these are just examples of the things I can measure. There's salinity with a nice strong front in salinity from fresher onshore, offshore to more salty onshore. We can measure currents. Down here is acoustic backscatter, and you can tell that the zooplankton, which are the primary scatterers, do care about this physical front. This is just an example. We can also measure chlorophyll fluorescence. You see the deep chlorophyll max, and also some evidence that the chlorophyll, that the phytoplankton knows something about the physical ecosystem. And then finally, we have dissolved oxygen up in the corner here, and where we're getting low levels at depth. Hypoxia is a bit of a problem off California. And then we can use these measures to form a proxy for aragonite saturation. That's a proxy relationship developed from Cal-Coffee data over the decades. And you can see that some of the low aragonite saturation water does get shallow and does affect some of the organisms that form shells. And that's another societally important issue. I will say that we're doing better with dissolved oxygen now. And if we're fortunate, we'll also put pH sensors on the gliders in the next few years. So we're working towards doing better with chemistry and biology. So now here's the sum total of what we've been doing for the last decade is we just keep putting gliders out there. And if we're doing our best, we have a glider on each line at all times. And this work is funded by NOAA, and so it has a performance metric. Yes? Anybody who's worked with NOAA knows you need a performance metric. And so here's mine, and I'm happy to show it. I take it very seriously. The performance metric is in the histogram, and each one of those colored bars accounts for how much the gliders on each line, and I want each one of those gliders to be, each one of those bars to be 1. So I have a glider on, if I did perfect during the year, I would have 1 glider year on that line. So if you add up all those 3 bars, I want to be at 3. And basically I've been able to do it. And we're doing it because I think it's because the design is good, and we work hard, and we make it a priority. So in other words, we've been successful in about the last 11 years to have 33 years of data on these lines. We've covered 250,000 kilometers and over 100,000 dives. So that's the data set, and it is all available online. So that's what we've accomplished. All right, so now I'm going to talk a little bit about sampling, and I'm going to geek out a little bit here. But I care a lot about how we sample the ocean. That's what making platforms like gliders is all about, is how do you get measurements out there? It's not a big deal, certainly, to measure temperature, and slighter bigger deal to measure salinity, but the goal is to get things out and cover the time and space scales you need. So this first example is I'm going to compare a glider to Cal coffee sampling. So we sample on the same lines now. And in this panel, this is from onshore to offshore, and from 2010 to 2013, 3 years. The black squares are every Cal coffee station on line 90 during that time. The blue line is actually a bunch of blue dots, and that's each glider profile during that same time. So really your goal in making measurements in a region like this on a line would be to fill up this panel with dots any way you possibly could. And so if you add up the dots, there are 165 ship profiles and 9,400 glider profiles. So gliders collected nearly 60 times as many profiles as Cal coffee did during the same time. So that has carries with it a certain advantage. If you look at it a different way, basically looking at the annual cycle, where in this lower panel you have onshore to offshore, but now all these data, same data, are plotted as a function of day of the year. You see a slightly different picture. Again, all the same dots are in both of these panels, but the only difference is the time axis is now day of year. And you can see the Cal coffee cruises. They tend to happen at the same time of each year. That's because they're run by people who have schedules, and especially the one before Thanksgiving you don't want to mess up. Because if you mess up the one before Thanksgiving, there goes Thanksgiving, there goes Christmas. And so that one tends to be at the same time every year. The gliders are out all the time. And so they actually, in this case, I think do a pretty reasonable job of filling, again, in this space of day of year against distance. And so we can get a pretty good measure of the annual cycle with gliders. So based on this, I've shown this to a lot of my friends in Cal coffee, and I'm willing to say something that I think I can back up, that at least with the things that we can measure on gliders, we can do a better job with gliders than with ships. Now here's the big caveat, is I can't measure everything with a glider. There's a lot of things you want to measure that you can only do from ships. So we're not replacing Cal coffee. Don't go home and tell your friends like near me that I said that this is better than Cal coffee, because it's not, because ships are amazing and you can do lots of things. But for the things that I can measure on a glider, I think it's better. I think it's a more efficient way to do the same kind of problem. So the other, again, now we're back to Argo, because Argo is another great way to measure the global ocean. Took the same 3 years of data from all of the lines that we have and plotted all those. Those are, again, the blue dots. And I grabbed from Argo every Argo profile in this region, which is a region that is being run by one of the regional models that our data go into. So again, you just count up all the profiles. We've got nearly 29,000 gliders profiles, and there are about 2,500 Argo profiles, so we got a factor of about 12 there. More glider profiles. And that's not really the most important difference. The most important difference is that because of Argo's design, it's designed for the deep ocean, they don't go onto the shelf, as they shouldn't. And so what the gliders do is they're great at connecting the coast with the open ocean. So it kind of fills that gap of connecting the coast to the open ocean and providing profiles in a region. All right, and then finally I want to answer briefly a question that was asked from the beginning of gliders, and that you would ask if you had the chance and I stopped talking. You would say, well, gliders are slow, man. I mean, they're so slow, what does that do? And the answer is it does something. So one of the tests we did long ago, published in 2011, is we did a line off Hawaii in the North Pacific with a glider. And this line covered from Hawaii up to 34 point something degrees, and it took from November to January about 2 months to do that. We then also took out a seesaw, a towed device that can be towed very quickly and do lots of profiles, and we did that same line in about 4 days. And then what I want to invite you is to look at these and just kind of cross your eyes and look at the colors. That's salinity that's plotted there. And I hope you get the idea that the large-scale structure is pretty much the same in this section that took about 2 months and this section that went 15 times as fast. So the large-scale structure just doesn't change that fast. So it's okay for large-scale structure. Do you see the difference, though? There's a really important difference. I don't know, do you see it? Look at these lines are isopycnals. They're contours at constant density. Do you see how this one's really wiggly right there? And there's the same one here, and it doesn't look near as wiggly. And the reason that is because the glider is going slow and profiling more slowly. It actually does a job of aliasing internal waves into our measurements. And so what it means ultimately is that we got to do something about that extra hash. And really, in the final analysis, it means that we can make measurements down to about a length scale of 30 kilometers. Even though we're measuring every 3 or 6 kilometers, really in the end we get a measurement every 30 kilometers. And we have to smooth some to get rid of those internal waves. All right, so now let's talk about a product that we've created with these data. So I'm just guessing most folks don't want those 100,000 profiles on their desktop. And I'm nuts, I do want them. But what I need to do is take those profiles and produce something that's more easy to look at. Essentially a modern day equivalent of an atlas. And so what we've done is we've created a climatology. It's basically an atlas that is a regular grid as a function of a grid in depth, 10 meters, in distance at 5 kilometers, and in time of 10 days. And so with this grid, which is in those 3 dimensions, now you can take any slice through time, depth, or distance and take a look at the data without having to care about individual profiles. Well, we have a lot of ways that we go about doing it. I'm not going to get into all the details, but the products are a mean field, the mean off California, an annual cycle, because if you're going to look at interannual variability like El Niño, you can't skip looking at the annual cycle. So we got the annual cycle, and then interannual variability, which is ultimately the thing we were after. At first, right now, we're focusing on the physical variables that we have the best handle on. And this was all available on Spray Data. You can go there and look at pages after page of an atlas, or you can download the data. And if I'm getting boring, please click on that, go to Spray Data and take a look at it. It was all published just last year. So this is a relatively recent product. So here we go. We get to do a little bit of coastal oceanography 101 of an upwelling system. And these are sections, the mean sections along line 90. This is the most observed Cal Coffee line. And you see temperature and the isopycnals bowing up near the surface, kind of a nice classic upwelling look to them. Here's salinity. Off California, the freshest water is at the surface than offshore. The saltiest water is near depth onshore. The reason we have that structure is because the current comes from opposite directions onshore and offshore. Onshore, there's what's called the California undercurrent, heading northward, bringing with it warmer, saltier water. Offshore, there's the southward California current. And so this is kind of a classic picture of upwelling circulation. This is line 80. I really hope this gets into a textbook one day. This is just like you might just draw if you were doing it on the board. There's the California undercurrent onshore, the California current offshore, salty water at depth onshore, fresher water near the surface, and this upward bowing of isopycnals indicative of an upwelling kind of system. So this is the mean. This is kind of step one. We've got a mean, and this is as solid as it can be. So that's step one. We got our mean. All right, let's move on to step two. Now we're going to get into some stuff I get excited about. This is an annual cycle. And here's the annual cycle. Now let me explain this picture. So it goes from onshore to offshore, and then the vertical axis is time from January through December. And this is the anomaly of temperature, different from normal over the year at 10 meters, that's quite near the surface, and at 50 meters. Okay, so if I were to show this to someone who lives in California, I was asked, when is the warmest water during the year when you go swimming on the beach? And they're going to tell me right away, that's in fall, that's September. The reason it's in September is because it's had all summer to cook, and it keeps warming up until it starts getting less sun. And so that's the warmest water of the year on shore, and the coolest water is in the winter. So that's no surprise. And that extends basically the same way all the way offshore with some little phase change. If you go down 50 meters to the depth of the thermocline, it's very different. The coldest water of the year is actually around the time it passes through zero at the surface. There's a phase change of about 90 degrees. And the coldest water during the year is in May, June. And the warmest water of the year is in the winter at 50 meters. And the reason that is that's caused by upwelling. Upwelling time on the west coast is in the spring. That's when we have the strong upwelling favorable winds, and they're least upwelling favorable in the winter. So you go down 50 meters and you're in a different world. The whole annual cycle has changed by about 90 degrees in phase. So that's the kind of thing you can see when you look at an annual cycle. Clearly, this is going to be important when we want to look at interannual variability. We have to know what's normal for the year. So just to take a look at a couple other variables, this is now the depth of an isopycnal. Blue means the isopycnal is shallow. So when there's upwelling, the isopycnal is shallow, and during the winter, when the upwelling is weaker, the isopycnal is deeper. That's why the temperature was as it was. And there are resulting changes in salinity. Actually, when the isopycnal gets shallower, it starts to get heated up by the sun, and there gets to be mixing, and it gets saltier, and as it gets pushed down again, it gets fresher. So there are all these effects that we can see this time on a constant density surface rather than a constant depth surface. And so now let's get back to the way I motivated this talk, and that was to look at climate variability. I've taken care of the mean, I've taken care of the annual cycle, and now I can look at what's left. And so what's left is the anomaly of temperature. And if you want to get down to the kind of thing we said we would do when we started the program, would be to create plots like this. You see these same kind of plots when you look at the El Niño report at the equator. They'll show you Hobmuller plots like this, that in this case show distance onshore to offshore, and then the whole record from 2007 up until the present. And what do you see when you look at this? So red is warmer than normal, and blue is cooler than normal. Do you see it around 2014 something happened? Well, we have had the warmest water we have ever had off California since 2014. It was a really unusual warming that started then, and it actually got into the news. It got widely known, at least on the West Coast, and it got the name the blob. Did you hear about the blob? Yeah, so the blob was this anomalous warming, and before it was called the blob, I was looking at my data saying, what is going on right now? Because we just saw all this warm water arrive, and it arrived everywhere. As you can see in 2014, basically this whole plot, from onshore to offshore, everything got red. You also see it down as deep as 50 meters as well. So these are the kinds of climate variability we can see. Now, if you look even closer, if you look at 50 meters, you can see this kind of initial warming that was called the blob happened, and then there was a little gap, and then this other kind of high was the El Niño we had in 2015-16. You can also see some evidence of the 2009-2010 El Niño. That's this red blob right there. So now we're able to look at the regional effects of these large-scale climate changes. And I hope you notice one thing that is really quite puzzling as well, and that is that it hasn't cooled down yet. So that change that happened in 2014 off California is still with us. And I don't think we quite understand why. So now let's take a look at this again, another slice through this climatology, and take a look at temperature and salinity anomalies, this time as a function of depth from the surface to 500 meters and time from 2007 till the present. So again, the colors are different from normal, and there's the blob right there. There was kind of a brief lull, and there's the El Niño. So there's a really big difference in the depth penetration. The El Niño changes extended down at least as deep as 400 meters, while the blob was a more surface intensified feature. We also saw changes in salinity. Actually, everything got a lot fresher during these past few years, mainly because the thermocline and the halocline were both pushed down. And so warmer water got deeper, and the fresher water that's typically at the surface off California also got deeper. So this difference in depth penetration was a real sign that there were different dynamics at work for these two events. So let's look at the same kinds of changes now on isopycnals. This is the depth of an isopycnal that's relatively deep. There's a deepening in response to the 09-10 El Niño. Here it's deepening in response to the most recent events. And then over here is the salinity on that isopycnal. And the interesting thing here is you look at this whole record and there's really just one event that jumps out at you. This is some very salty water on this isopycnal during the El Niño. One of the effects of the strongest El Niños is that southern water is brought into our region. And the best way I know of to identify it is with salinity, because the only place you can find salty water in our part of the world is to the south. So when you see this influx of salty water, that's a sure sign that this is the strong El Niño. And this was surely one of the strongest El Niños we've had since the one in 1982-83. So a very strong indication of oceanic advection. The reason we care about that, if you don't like salinity so much, is also because that advection brings in southern species. And so we see an influx of species from the south brought by the same current that brought that salty water. And so finally, I'll end this discussion of El Niño with a few words about indices. So the advantage of indices, again, you don't want 100,000 profiles, and you don't even want to have to look at the climatology. What you want is just one number, please. And so here's a one number, please, kind of time series. And so as a function of time, I have two indices in this panel. The black line is the Oceanic Niño Index. This is sea surface temperature in the equatorial Pacific, and it's the index that NOAA uses to decide whether or not there's an El Niño. Basically, when this black line it's a temperature anomaly, when it's bigger than 0.5 degree C for at least 5 months, that counts as an El Niño. When it's colder than -1 degree C over at least 5 months, that's the La Niña. So the black line is really what NOAA uses in their declarations of El Niño. The red line is temperature at 50 meters in the Southern California Bight, as measured by the gliders in the inshore 200 kilometers. Before 2014, if you look at those two lines, they're very strongly correlated. And that was a bit of a surprise to me at first. I looked at it, was like, wow, I can tell what the equator is like right here off of California, or vice versa. It's extremely strongly correlated. The big event, of course, was this El Niño in 2010. It was one of those El Niños that was a bit unusual in that it was concentrated in the central Pacific. But then even some of these little fluctuations you can see. Then starting in 2014, it was a really interesting year. There started to be an increase in temperature at the equator, and I don't know if if you're an El Niño aficionado like I am and watch the weekly reports, you would have seen in 2014 that the models and NOAA was saying there's a 70% chance of an El Niño this year in 2014, and then it stopped. It just stopped, and 70% of the models were wrong. 30% were right. What happened instead is that thing we called the blob. So the warming continued in the North Pacific, really widespread. So there's the blob. And so there was the blob. Then the following year, we had a full-fledged El Niño, the third strongest really since the 1980s. And it was strong both at the equator and off California. And those were the warmest temperatures we've ever observed off California, at least as measured by the Scripps Pier, and as far as I can tell too. Since then, the equator has gone back to normal, but we have not off California. We've kind of entered a different climate regime, maybe. I don't know. But it is warmer than it just has not gotten back to normal. Things have changed. This plot over here is a measure of surface temperature, 10-meter temperature on all the lines. That's all these colorful lines. The black line, again, is the Oceanic Niño index. I guess the only point I want to make here is before 2014, if you can see a correlation there, more power to you, because I can't. But anyways, in 2014, they all got the same message, and it warmed all along the California coast all at once. And while it's kind of waffled around since then, it has stayed warm. And so something changed in the North Pacific in 2014. We're still trying to figure out what it was. But having these regional observations allows us to tell that it's a real thing. All right, so just a few words now about how glider data is used. So one of the major uses of these data is to assimilate into models. These data are assimilated into several models. I could probably name off the top of my head 4 or 5 that I know are taking these data in right now. And that's really a great use of these data because the data I have are on these lines, and the model, of course, has values everywhere. And so this is an example that shows the velocity, mean velocity measured on each one of our lines. You can see the California undercurrent near shore and offshore the California current. And all the black arrows are the currents from a model that we're actually using at Scripps. And if you look at them, you can say that they care about each other. And what's interesting is that the model does not assimilate velocity. So this is a fair comparison. The model does not assimilate these data. It only assimilates temperature and salinity. And you can see that the undercurrent is very continuous. There's a place where there's a minimum in current that agrees between the gliders and the data. And then there's the California current heading southward offshore. So ultimately, the goal is an observing modeling system, where we can bring in these data all the time, where there are models that are taking them in and making predictions. That's how we'll make predictions. And then it allows us to assess all the terms in the balance. We'll be able to tell what's advection and heat, whether or not we have stronger than normal upwelling, and how the atmospheric forcing comes into it. So we're starting that. We have a paper just submitted on trying our first step at evaluating this particular model. And then we're going to move on to be able to see if we can say definitively how the water gets warmer during both the blob and during El Niño. So, final slide. A lot of us have been doing a lot of work, including you folks at USF. And here's just a collection. It's certainly not complete, but it's a collection of a bunch of the glider tracks going back to the early 2000s in the US. And you can see that gliders have covered pretty much all the coast. There's a place there where we haven't had gliders too much, but we got a lot of coverage. We got a lot of coverage along the US coast. The thing is that this is a composite of everything since 2000. And so the only things that are sustained right now, to my knowledge, are what we're doing now off California and this work in the Gulf Stream. And I guess the vision, you know, if we really wanted to do the job along the US coastline, is we know we can do it, it's just to continue to do it. And then we would have a regional network, the same density of profiles that we have, like off California, along the whole US coastline. And it's really just a matter of wanting to do it. It's not whether we can. So I'm just going to say it's possible. Whether it'll happen, I don't know. But I know we could do it. So let me just conclude. And I told you a little bit about the climate off of California. We talked about the underwater glider network. It's been going on now for 11 years. We have a climatology on each line. Allows us to do the mean, the annual cycle, and anomalies. And I just close with the question, are we going to be able to do this everywhere in the future? I think we can, but we just have to want to. With that, let me ask for questions. Thank you very much.